Hi there, my name is Samantha Canode. I'm a sophomore at Baker College studying cyber defense. My goal here today is to teach you about IP subnetting and VLSM. This is my final project for advanced routers and routing, also known as NET 2250. To understand how IP addresses work, we first need to know how binary works. Since computers use electricity, the electricity that runs through microchips on a computer is either set to on or off, 1 or 0 respectively. This is known as binary or base 2. Our numerical system is base 10 since we use 10 symbols, 0 through 9, to represent our numbers. In the base 10 system, as soon as we get to 10 or an exponent of 10, we add a digit to the left. Since there are 10 symbols, each new digit has a value of 10 times greater than the digit to the right. We can simply replace 10 with 2 in those sentences, and the same rules will apply. This means that in the base 2 system, as soon as we get to 2 or an exponent of 2, we add a digit to the left. Since there are 2 symbols, each new digit has a value of 2 times greater than the digit on the right. With binary, we only have 2 symbols to work with, 1 and 0. Binary usually exists in octets or sets of 8. In this chart, we can translate base 10 to base 2 numbers up to 255 and back pretty easily. I'm going to write an example of a binary number in here. From binary to decimal, all we have to do is put the binary number into this chart and add up each number that has a corresponding 1. That means we're going to take 128, 16, 8, 2, and 1 and add them together. This gives us a total of 155. To translate a decimal into binary, we'll take a number to translate, we'll use 200, and ask, can I fit 128 into this? The answer is yes, so we'll put a 1 here and subtract 128. That gives us 72. Next we'll ask, can I fit 64 into this? The answer is yes, so we'll take 72 minus 64, which gives us 8. Next we'll ask, can we fit 32 into this? Which is no, because we only have 8 left, which is also no for 16. We have exactly 8 left, so we'll put a 1 here. The rest will be 0 because we can't fit any of these numbers into 0. So we've translated 200 into binary, which is this right here. With a little bit of practice, you'd be able to easily translate them into seconds, especially when you start seeing recurring numbers that make the process faster. Now that we've gone over binary, we can get to IP addressing. Now we can start with the discussion of IP addresses. You need one to communicate with other computers or servers. Instead of using a geographical location for your address, use a unique string of numbers called an IP address. IP addresses are represented by 4 octets of binary numbers divided by periods. An example is something like this. Using the conversion trick from before, we could translate this IP address into binary and back. IP addresses all belong to a class. The class is determined by the first octet of the IP address, or the first 8 bits. So our example from right here is a class C address because it falls within this range right here. IP addresses can also be public or private. Private IPs are internal and only valid on LANs, not the internet. Public IP addresses are external, globally unique, and valid on the internet. Private IP addresses can be A, B, or C and fall within a specific range within those classes. E is experimental, and D is for multicast traffic, which is for sending information to several destinations at once. You might have noticed that 127 is missing from these ranges. While still Class A, 127 is known as loopback, used for testing things like client-server software on a machine using itself. Now that we have IP addresses down, we can talk about classful and classless addressing. Classful is obsolete and no longer used. They only use default subnet masks. This means you'd be stuck with all the default hosts you're given in a class address, no more, no less. If you're using a Class A, you'd be wasting millions of addresses. This is where classless addressing comes in, or VLSM. VLSM stands for Variable Length Subnet Mask, lets you perform subnetting. Subnetting is short for subnetwork and it is the process of taking a large network and breaking it into several smaller networks to make them easier to work with. Subnetting reduces network traffic, enables users to access a work network from their homes, and helps surpass constraints in a LAN like the max number of permitted hosts. When we're working with subnets in VLSM, we can divide a single class A, B, or C network into smaller portions. Those subnets can also be divided or subnetted further. All machines with an IP address will also have a subnet mask if it wants to communicate with other machines, regardless if it's subnetted or not. Subnet masks are used by local machines to determine what subnet it's a part of. Subnet masks relate to their IP addresses. Subnet masks are actually a string of ones followed by zeros. So using what we learned before, we could take this right here. We would know that translating 255 would be 8 ones, and the rest would be zeros. The ones represent the network portion of the address, while the zeros are the host portion. Subnetting is just taking the original subnet mask and adding bits, known as ones, to create more networks. If you convert a subnet mask to binary and add ones in places of zeros, you're subnetting the network. Since subnetting involves borrowing bits from the network segment to use for the host segment, you can move the line between network and host bits to create more or fewer networks and hosts. If we move this line from here to here, there's more networks and less hosts. If we move it to the left, there's less networks and more hosts. Subnet masks can be written two ways, dotted decimal notation and slash notation. Since it's known as decimal notation, it's written like how we would normally see numbers. We can see up here the default class C subnet mask would be 255.255.255.0. To write one in slash notation, also known as CIDR, which stands for classless interdomain routing, you first convert the subnet mask to binary. We know that these are all 8 ones. .0. Now that we have the subnet mask in binary, we simply count the number of ones in the subnet mask. There's 8, 16, 24. Since there's 24 ones, that means it's a /24. We can then finally write the IP with the subnet mask. We can use an example one, the default class C, /24. Now that we know about IP and subnetting, we're going to apply all this information to an example network. This is a small WAN, or wireless area network topology. Our network consists of two LANs, or LAN area networks, connected together. Each LAN has its own router, switch, and varied number of hosts. The routers connect the geographically separate LANs to make a WAN. We're going to subnet this one giant network to conserve IP addresses, reduce network traffic, and simplify things. For starters, what IP class are we going to use? If we aren't expecting the number of machines to grow exponentially, we'd like to conserve space. First, we'll take the number of IPs we need and add them together. That includes the 50 hosts we have here, the 30 hosts we have there, and the 2 IPs we will need for right here. That's 82 addresses. We're going to use private class C 192.168.3.0 for our base network. This choice is due to the fact that we don't need more than 254 addresses, the default maximum number of hosts you can have on a class C network. Our first subnet will be the one with 50 hosts because we always want to start with the largest subnet first. This makes it easier to allocate space correctly, making it easier to manage and support future modifications. We need to find the smallest size number of bits to borrow that can fit 50 IP addresses. We're going to follow these 5 steps. Determine the default subnet mask. The default subnet mask for class C is this right here. we're going to break out the available bits. Since we're using Class C, we have the last octet available right here. We'll figure out the number of bits needed to represent the number of hosts. We need to take into account the extra 2 addresses needed for each subnet. This is for the address of the subnetted network, which is the network ID. That'll be the first one, as well as the broadcast, which is the last one. The smallest number we can choose and still have room for 52 hosts here is 64. Now we'll determine the new subnet mask. Since we went with 64, that's 2 bits in, so we'll be changing these 2 to 1s. That leaves us with this, which is a /26. Now we want to figure out the network ID, host range, and broadcast. Since this is our IP, this right here is already the network ID. We're going to add 64, so to the end, that would be the next subnet network ID. If we subtract 1 from this, 63, that'll give us our broadcast ID. Everything between 0 and 63 would be the usable host portion, which is 1 to 62. That means we are left with /26 for this network. We'll repeat these steps for additional subnets. It might sound like a lot, but we already have steps 1 and 2 done. Our next subnet is 30 hosts, so we found out from the last exercise, this will be our network ID. The default subnet mask is still the same right here. We need to break out the available bits right here. Now we need to figure out the number of bits needed to represent the number of hosts. We need 30 plus 2, which is perfect right here, 32. That's 3 ones that we'll be adding to right here. This is our new subnet mask, which there are 27 ones, so that's a /27. Now we need to figure out the network ID, host range, and broadcast. This is our network ID right here. If we add 32, we'll get .86, which will be the next network ID. We subtract 1 from that, we'll get 85, which will be our broadcast. If we add 1 to our network ID right here, we'll get 65 to 1 less than the broadcast, which will be 84. Almost done. The last subnet for the connection between the routers only needs 2 usable host addresses. This is because they require a default gateway assigned to the ports connected to each other. Default gateways are typically the first address in the usable host portion of a subnet and are where data is sent when the destination address doesn't match anything on the current network. So we'll start. We determined the default subnet mask. It's still C. We broke out the available bits right here. We need to figure out the number of bits needed to represent the number of hosts. We need 4 because we still need the 2 for the network ID and the broadcast. So 4 right here works perfectly. Then we'll add 6 ones. And that brings us up to of 30 ones, which is a /30. Now we get to figure out the network ID, host range, and broadcast. We found out from the last problem, this is our network ID. We know that if we count up by 4 right here, 2.90, which would be the next network ID, we take 1 from that, we get 89 as the broadcast, and everything between 87 to 89 is the host portion. And that's the last subnet we're using. You would then want to take all the information you've gathered and put it into a table for reference if you haven't already as you were subnetting. Here's our WAN in all of its glory, complete with 3 subnets. Here's the table. I hope this video was informative and successfully taught you the ins and outs of IP addressing in VLSM. Thank you for watching.